Our fellow learners, this is Cameroon GCE ordinary levels, excuse me, chemistry 0515. In this video, we are going to continue with June 2024 paper 2. And we will be starting with question number 4. On question number 4, as I told you, I am going to take time and explain some basic concepts which you will use in your subsequent or you will use in your exams. My goal to you is not just to give you answers, but to make you understand the concepts. Make you understand the concept that you can apply during the exam. But before we go ahead, I would like to appeal to those who have not subscribed to my channel to take some time now and subscribe. Because when you do that, the rest of the video, you will have them directly. Thank you very much for taking your time to subscribe. Let's get started. We are on question number 4. The question reads, an element W, where W is not the usual symbol, exhibits isotopy. The isotopes are W, that is isotope of 47, W47, and W49. Have relative abundances of 60% and 40% respectively. What is isotopy? Yeah, this is what I have been telling you. You should know all this. You should know the difference between isomers, isotopy, allotrope, so that you are not embarrassed in the examination room. What is isotopy? Isotopy, as stated, iso means the same. Iso means the same. So what is isotopy? Isotopy can be, this is a phenomenon that is used this is a phenomenon that is used to describe the occurrence. A phenomenon that is used to describe the occurrence of atoms of the same element with the same atomic number but different mass numbers due to what? A difference in the number of neutrons. Atoms of the same element with the same atomic number but different mass numbers due to a difference in the number of neutrons. Let me put it here like that for you to see. Let me say for A. We say their atom occurrence, that is 1. Occurrence of atoms of the same element with the same atomic number but different mass numbers. Due to a difference in the number of neutrons. Okay, For example, we were given this one. See what is happening there. We were given 47 and that is 22 for W, and this other one 49 and what, and 22 for the other isotope. These are two isotopes as you see them like this, 47 and 49. It's just as they tell you, chlorine 35 and chlorine 37. Now, we said isotopy is the occurrence, it's a phenomenon to describe the occurrence of atoms of the same element, there's W, with the same atomic number, that is 22, but different mass numbers, that is 47, 49, due to what? A difference in the number of neutrons. And the person who is causing this difference in the number, the person who is causing the difference in the difference in the mass number is the number of neutrons. So if you give the definition in the exam, you are fine. You have all your marks. The second one, what makes the two isotopes different? We have already answered it. We have already answered that one. And what makes it number of neutrons? So you can say, you can put it here. What makes the two isotopes different? You can put it as the number of neutrons. The number of neutrons. What makes the two isotopes different? The number of neutrons. That is, they have different number of neutrons. They have different number of neutrons. So the number of neutrons is the one that is causing all this. Calculate the relative atomic mass of W. Okay, the relative atomic mass of W can be calculated by this. You have, since we have given the relative abundances of them, you can say it is 60. You can say 60. You can say the 60% was for 47. So you can say it is 60. 60 all over 100 times 47. That is for that isotope. Plus 40 all over 100. That was for 49. You add all this, we will have 28.2 plus 19.6, and that will be equals to what? The relative atomic mass. The relative atomic mass of W will be equals to what? Will be 47.8 atomic mass unit. It will be 47.8 atomic mass unit. Let's move on to the B part of it. Consider the reaction had an aqueous. AQ is aqueous. That is a solution. It's a dilute solution of hydrochloric acid. Aqueous solution of hydrochloric acid plus aqueous solution of hydrochloric acid plus aqueous solution of sodium hydroxide to give a salt, which is sodium chloride and water. This is an exothermic reaction. Why? It has a negative value. Okay, then this the reaction B. We have ethanol. This is ethanol plus the liquid form of ethanol, or what you call spirit, reacting in oxygen. That is a combustion reaction. You are going to have a complete combustion. You are going to have 2 moles of carbon dioxide and 3 moles of water. It is still a combustion reaction. Based on the reaction, identify the type of reaction represented by A. Now, the type of reaction represented by A, you look at it. Okay, you must have been told that when an acid reacts with a base, sodium hydroxide is an alkali. In other words, we call it a base. And hydrochloric acid is an acid. When an acid reacts with an alkali, it is a neutralization reaction. It is a neutralization reaction. Heat is being evolved. All are exothermic reaction. So we call number 1 is a neutralization reaction. Number 1 is neutralization. A neutralization reaction. This is a neutralization reaction. B, it is a complete combustion reaction. So we call B as complete combustion reaction. Any reaction in oxygen to give a gas, and that we call it a combustion reaction. Combustion reaction. And we call it is a complete combustion because every complete combustion gives carbon dioxide and water. So we say complete. It's a complete combustion. Now, based on the energy changes, identify the type of enthalpy change represented by A and the enthalpy change represented by B. Okay. If you look at the enthalpy changes A and B, okay, identify based on the enthalpy change, identify the one represented by A and B. A and B are all exothermic reaction. Why do I say they are exothermic reaction? Because the energy change, delta H, that is change in energy, is negative, kilojoule per mole. Change in energy, delta H, is minus 1273, and which is negative. So all of them are exothermic reaction. What is an exothermic reaction? An exothermic reaction is a reaction in which energy is evolved, heat is evolved to the surrounding. Okay, so A and B are exothermic reaction. A and B, A and B, we'll say they are all exothermic reaction. The exothermic reactions. Because energy is evolved to the surrounding. Okay, define enthalpy change. What is enthalpy change or energy change? Energy change, which is delta H. The delta H you see here, this is what we call energy change, delta H. Energy change is the amount of heat evolved or absorbed in a reaction carried out in a constant pressure. I can say, let me put it this way. Let me put it as the enthalpy change That is delta H. Enthalpy change is the amount the amount of heat evolved, that is released, evolved or absorbed, in a reaction. In a reaction carried out at constant pressure. Okay, I said enthalpy change is the amount of heat evolved or absorbed in a reaction carried out at constant pressure. Okay, let's go to question number the fourth part of it. What volume of carbon dioxide will be evolved from reaction B when 5.2 grams of ethanol is burnt at room temperature? Okay, room RTP, room temperature. Now, at room temperature, you now see the calculation we are going to do now. At room temperature, you should know that the reaction, let me go here. Let's go here. Let me say here. Yes, you can get it this way. Okay, let me start here with you have to write use the equation you have been given, the reaction you have been given in calculating this. So the first thing is I need to write my equation. When you write your equation, you are set to start. Your equation is ethanol is same CA5 sorry, we are talking of, we are not going back to pentane, something pent. Ethanol E is C2 H5 OH. Of course, that is liquid. When the combustion of it, okay, we have oxygen. That is a gas. Okay. Carbon dioxide and water. The water that is being formed. Let's balance our equation. The balancing is 3. Here you have 3. Here you have 2 carbons. And then you have how many hydrogens? 6. So 6 times 3. Okay. That is your equation. Now we are involved with ethanol and carbon dioxide. Ethanol and carbon dioxide. So the equation is between this, the thing is between this. So we have here, from here, these are the people we are targeting. This N and this N. This N and this N. So our question says, what volume of carbon dioxide will be evolved from the reaction B, which we have just written, reaction B which you have just written, when 5.2 gram, we are now talking of 5.2 gram at room temperature and pressure. Okay, look at it keenly, my fellow learners. This is how you write your equation. because before calculating, you are going to be given scores for this. 2, you number the number of moles. The number of moles are what? Okay, moles of ethanol that are being burnt. What are the number of moles of ethanol that are being burnt? Remember to have the number of moles, the mass divided by the molar mass. So the first thing you are supposed to do is you need to have the molar mass of ethanol. The molar mass of ethanol is 12 times 2 plus 5 hydrogen. Hydrogen is 1 times 5. So 2 times 12 plus 1 times 5 plus 16 and plus 1. That gives us a total of 46 grams of ethanol. Then carbon dioxide. The molar mass, the mass of carbon dioxide has been given. So, the mass of that is being burnt has been given. So, the number of moles, we now come here and we start here that moles, number of moles. Moles of moles. I'm taking a longer method so that you can better understand. The number of moles here will be moles of ethanol. Mole of C2H5OH will be what? The number of moles here will be that are burnt will be 5.2 gram all over 46 gram times 1 mole of ethanol all over 1. So we say times 1 mole of ethanol all over what? All over 1. So the gram will, this one will cancel this one will cancel this. So 5.2 divided by 46 times 1 mole. It gives us the number of moles will be what? The number of moles will be 0.1130 moles. 3 moles of ethanol of C2H5OH. Okay, now we have got the number of moles of ethanol that have been burnt. Moles of ethanol burnt, we have got them. Now let's use simple proportion. We are in the exam, we have to be very fast. The next thing we do is use simple proportion. And the simple proportion here is what? Say this how I do it. The simple proportion here is, take it like this. If 1 mole from the equation, there's only 1 mole of ethanol here. If 1 mole ethanol, a 1 mole C2H5OH will give you in the reaction 1 mole here. In this reaction, 1 mole here is giving you 2 moles of carbon dioxide. Will not give me 2 moles. Will not give me 2 moles of carbon dioxide. Therefore, okay, we have calculated the number of moles here that were burnt. Therefore, 0.1130 moles of C2H5OH will give what? It will give us, let me say, a number X. We don't know. And how do we get that? We will have to look for the value of X as the unknown. X, which is the unknown, will be what? It will be 0.1130 moles of C2H5OH times what? Times the 2 moles of the carbon dioxide that were produced times 2. It gives us, this is 0.2261 moles carbon dioxide that were being produced. But now, remember that I told you in a previous video that at standard temperature and pressure, any gas occupies a volume of 22.4 dm cube. But at room temperature and pressure, any gas 1 mole of any gas, 1 mole of any gas will occupy a volume of 24,000 cubic centimeters or 24 dm cube. So now, if 1 mole of carbon dioxide is occupying, let me put it here, that's the mole. This is the number of moles we have got for carbon dioxide. Now, if based on the principle, but 1 molar volume of a gas, 1 molar volume, 1 molar volume of a gas at room temperature and pressure, at room temperature or pressure, occupies what? It occupies 22, occupies 24,000 cubic centimeters. If 1 mole of any gas occupies 24,000 cubic centimeters, therefore this volume will occupy what? So all what we are saying is the molar volume of a gas. So if 1 mole of a gas will occupy this volume, then let's say it was carbon dioxide. 1 mole of carbon dioxide will occupy what? 1 mole of carbon dioxide will occupy this volume. Then the number of moles that are here will occupy what? The same simple proportion. Then 0.2261 moles of CO2 will occupy what? We don't know. So in that case, we have to multiply what? We have to multiply which will be equal to what? We are multiplying 0.2261 moles of carbon dioxide, times the cubic 24,000 times 24,000 cubic centimeters. Yeah, times 24,000 cubic centimeters divided by what? Divided by 1. So if I said divided by 1 mole, so I said if 1 mole, I said here that if 1 mole, which is a molar volume, if 1 mole of a gas, that is of carbon dioxide, occupies this volume, then this number of moles of carbon dioxide that were produced will occupy what? So it will be 0.2261 moles of carbon dioxide that was being produced times the molar volume, which is 24,000 cubic centimeters, divided by the 1 mole. So now, in cancelling out this, what we are going to have will be the number of moles here. The number of moles here, in cancelling out this here, okay, this number of moles here will cancel this number of moles here. We are now looking but for the volume that is now left. And our volume, based on our calculation, will be what? Our volume based on our calculation will be 5,426.1 cubic centimeters of carbon dioxide. Or you can divide it by 1,000. That will give you 5.426 dm cube. So 5,426.1 cubic centimeters of carbon dioxide gas that will be produced. If you did it like that, then you are right. So once more, in such a calculation, what you need to do in such a calculation is, I told you, you have to first of all write your equation. After writing your equation, you now look for the number of moles because the mass of ethanol was given, and you have to divide it. So in order to divide it, it is mass all over the molar mass. And the molar mass is, you need to put 2 times 12 plus hydrogen is 1, 5 times 1 plus oxygen is 16 plus 16, and the hydrogen is 1 plus 1, a total of 46. So 5.2 divided by 46, then times 1 mole, and we will have 0.1130 moles of ethanol that was burnt. Then now we want to know if this amount was burnt, then 1 mole is in terms of moles. Okay, a 1 mole of ethanol can give, from this reaction, a 1 mole of ethanol can give 2 moles of carbon dioxide. Then the burnt number of moles, a 1 mole of ethanol can give this. Then this number of moles, that is 5.2 grams of ethanol that gave this, ethanol that was burnt, will produce what? Will produce a certain amount of number of moles of carbon dioxide. We did our calculation gently, and we got the volume of carbon dioxide that was produced, the number of moles produced was 0.2261. But we have been asked to calculate at room temperature and pressure. And I said 1 molar volume of a gas at room temperature and pressure occupies a volume of 24.00 cubic centimeters. But it is at standard temperature and the pressure, STP, that it will be 22.4. But this one is 24. So now, if one volume of carbon dioxide will occupy this at room temperature, then this number of moles of this number of moles of carbon dioxide will occupy what? This is the volume, and our answer is 5,426.1 cubic centimeter, or 5.426 decimeter of the gas. Thank you, and that will be our answer. So that is the answer there. You went there. That is the answer for this. It took us a longer way. Okay, let's go to question number 5. Question number 5 has to do with question number 5. It has to do with industrial manufacture of ammonia. In question number 5, there are a lot of things we are going to put into application. 1, using the flow chart. So from the question, it is written, the flow diagram below shows the main stages in the industrial manufacture of ammonia. So, okay, look at the flow chart very well. You'll see sources, the source of the raw material. Of course, you know where hydrogen is got, and you know where nitrogen is got. Okay, there's a compressor where the two will come and meet. You know, there are reactors, the temperature at which that reaction is taking place, the pressure at which that reaction is taking place, and the role of ion in it. No, ion is a finely divided ion. It's a finely divided a finely divided ion is the catalyst that is being used in this reaction. Now it goes back to the cooler, comes back again, and before it is finally released for collection. And if it is not collected again, it is recycled again back to it again. So the question now says, A, identify the sources of raw material X and Y. Okay, this is not new to you. I am certain you have this with you. So X is nitrogen. Nitrogen is obtained from from the fractional distillation of liquid air. So we can say X is nitrogen is obtained. Nitrogen X is obtained. Okay, I can say identify the source of raw material X. Obtain, can say obtain. The source is fractional distillation. That's the main answer. Obtain obtained from the fractional distillation fractional distillation of liquid air. So now, your main answer here is fractional distillation. Fractional distillation of liquid air. That's the answer there. Fractional distillation of liquid air. Then, if we go to to Y is hydrogen. Oh, is also obtained from what? Nitrogen is obtained from natural gas. Okay, you can put it there like that. Obtained from natural gas. We are natural gas. I'm talking of hydrocarbons by cracking. Hydrocarbon by cracking. So when there's cracking of hydrocarbon, large hydrocarbons, cracking is the breaking down of large molecules of hydrocarbon at high temperature into smaller ones. So now that is cracking. Cracking. Yeah, cracking of hydrocarbons. Okay. Natural gas, that is obtained from natural gas, that is from hydrocarbons by the process of cracking. Okay, let's go to B1. B1 is B1. Write a balanced chemical equation for the reaction occurring in the reactor. The equation that is occurring in the reactor. But there is something I'll say before I go to that one. Before I go to that one, there's something I just need to add here for the purpose of revision. I said fractional distillation of air helps to separate the different components of air in their forms. You know that the air is a combination of different gases. So through fractions, just the word fraction, through fractions or fractional distillation, it helps to separate the different components of the air into their different forms. It will separate nitrogen. It will have about 78%. It will separate oxygen, which has about 21%. It will separate carbon dioxide, which has about 0.03%, and noble gases like argon in 1%. Let's move on. B. I'll write a balanced chemical equation for the reaction in the reactor. Okay, the reaction in the reactor will definitely be this. For the reactor, where is B? We will have in the reactor we have nitrogen. That is nitrogen. There's nitrogen there. Nitrogen is a gas. Always put the state of the matter plus hydrogen plus hydrogen, which is a gas. Now, this is in equilibrium. It's a reversible reaction. You need to draw it like that to show that it is a reversible reaction. Then you have ammonia that is being produced, which is still a gas. We can now go ahead to balance our equation by writing ammonia here is 3, so we have to put a 2 here for this reaction to, so it's 3, let me say 3 here. Yes, hydrogen are, yeah, we'll put a 3 here. Let me just say 3 here. Yep. If there is a 3 there, we have, how many hydrogens are here? There are 6. Here it is just 2. I mean, just 3. So we need to put a 2 here to balance it up. So we have 3 times 2, which is 6 hydrogen. 2 times 3, which is 6 hydrogen. But nitrogen is there. Nitrogen is 2 here. Nitrogen is 2 here. So our equation is balanced. Now let's move on again. What is the function of the ion in the reactor? When I first of all lecture you about this thing, you should know that ion is using as a catalyst. Is finely divided ion that is used as a catalyst in the reactor. So what is the function of ion in the reaction? You don't need to write too much. Just say act as a catalyst. Finish. You don't need to go write much. Ion is acting as a catalyst. So let's move to the third one. The third one says, how is the wastage of the unreacted nitrogen and the hydrogen minimized? The hydrogen, the unwasted hydrogen, and the one that is not used, how do we reduce it? How do we minimize it? You know, these are the gases. So the gaseous ammonia formed is downward. The gaseous ammonia that is formed is liquefied and constantly removed from the chamber as it is produced, so that the unreacted nitrogen and the hydrogen are passed over to the catalyst again. Just as I said, if this is not removed, if ammonia is not being removed, it is recycled back, and the unreacted one will still unreacted nitrogen will still remain there. But as soon as as soon as ammonia is formed, it is taken off so that the unreacted nitrogen and the hydrogen are reacted to form more ammonia, more ammonia. So we said the only way to minimize it is that the gas form is liquefied and constantly removed, so that the unreacted nitrogen and hydrogen are passed over the catalyst again. Let me put it here. Yeah. The only way to minimize this, I said, the ammonia form is liquefied and constantly removed from the chamber, so that the unreacted nitrogen so that the unreacted nitrogen and hydrogen are passed over the catalyst. Over the catalyst again to form more ammonium. So the only way you can minimize that is, as I said, the ammonia formed is liquefied and constantly removed from the chamber, so that the unreacted nitrogen and hydrogen are passed over the catalyst again for more ammonia to be formed. What is the function of the cooler? The function of the cooler, as you see, the cooler has about two functions. It helps to remove heat from the gaseous ammonia, thus condensing it into the liquid form. Then also cooling decreases the vapor pressure so that the liquid ammonia remains in the same state at a reduced pressure. So we can now say that one, what is the function of the cooler? We have two functions. The functions, or I'll give the two, then you select one. One, the first function is one. I said the cooler helps to remove heat from the gaseous ammonium. Helps to remove heat. Helps to remove heat from the gaseous ammonium. From the gaseous ammonium, thus liquefying it. It helps to remove heat from the gaseous ammonia, liquefying it for collection. Gaseous ammonia for collection. Yeah, gaseous ammonia to liquefy it for collection. Then the second one is cooling decreases the vapor pressure. Cooling decreases vapor pressure. Cooling helps to decrease the vapor pressure. Cooling, it decreases the vapor pressure. It decreases the vapor pressure so that the liquid ammonia remains in the same state. Remain in the same state at a reduced pressure. So now, what you just need here is it helps to remove heat from the gaseous ammonia for collection. Now, two, cooling also decreases the vapor pressure so that the liquid ammonia remains in the world. It remains in the same state at a reduced pressure. Okay, Now, the ammonia obtained is used to produce the nitrogen fertilizer, which is called ammonium nitrate. It has a molar mass of 80. Now, name the substance that is reacted with ammonia to form ammonium nitrate. Of course, the substance that goes with ammonium nitrate, ammonia, react with ammonia to form ammonium nitrate. Ammonium nitrate, there is a nitrate there, and nitrate is nitrogen and oxygen involved. So it has to come from an acid. It must come from an acid, and the acid involved in it is nitric acid. Is the nitric acid that is involved in it. Nitric acid is the one involved in this. So nitric acid is the one. Name the acid is nitric acid. Nitric acid. That is HNO3. Okay. So UNA levels, and when ammonia reacts with nitric acid, this is what is going to be formed for note for revision purpose. So you will have nitric acid and plus, let me say, ammonium, and we will have a salt that is being formed, which is ammonium nitrate. That is that. Okay, let's go. That is for revision purpose. So it was nitric acid. That was our answer. Number 2, calculate the percentage of nitrogen in ammonium nitrate. Percentage of nitrogen in ammonium nitrate will definitely be about 35% from my calculation here, because the percentage, if you look at the ammonium nitrate here, there is how many nitrogen atoms are here? 1 and 2. Nitrogen is 14, and 14 times 2 is 28, and the molar mass here is what? Is 80. So now 28 over 80. So what I will say is this: nitrogen, the percentage of nitrogen by mass, all over the salt. What is the salt? Ammonium nitrate times 100 over 1, which, if we go further, we will have 28 divided by 80 times 100. I think we'll be having 5%. Oh, thank you. I think that's great. So, fellow learners, we have come to the end of this section. We will continue with the other section that will be coming up in the next edition. So once more, for those of you who haven't subscribed to my channel, please get up and subscribe. Take some time now and subscribe to this channel so that you will have subsequent videos that will be coming out. Thank you very much. Have a nice day. Good luck in your exam.